Our world is just humming with invisible forces. Things like radio waves, Wi-Fi, heat, they're all around us, but we can't see them. But what if we could? What if we could give ourselves a new kind of superpower? Well, today we're going to dive into the amazing science of how we're learning to see one of the most common invisible forces there is, sound.
Okay, we've all been there, right? There's that one little rattle in your car that's driving you absolutely crazy. Or maybe it's a weird hum coming from your fridge in the middle of the night. You can hear it, you know it's there, but for the life of you, you cannot figure out exactly where it's starting. It's this frustrating little mystery. And believe it or not, it's a mystery that engineers have to solve on a massive scale, every single day.
See, for the people trying to design quieter products, this isn't just some small annoyance. It's a huge engineering problem. They basically have to become noise detectives, and the sound itself, that's their invisible culprit. I mean, just imagine trying to find the one tiny faulty part in a jet engine while it's running. Or in a giant complex piece of factory machinery. You've got hundreds of parts all moving, vibrating, and making their own sounds. It's like trying to solve a crime with no witnesses and no fingerprints. So, how in the world do you catch a culprit you literally can't see? Well, you give yourself a new way to see. And that's exactly what scientists have done. They've developed this truly revolutionary tool that lets them, in essence, take a picture of sound. It's got a pretty fancy name, Near-field Acoustic Holography, or NAH for short, but you can just think of it as a super special kind of camera. Instead of using a lens to capture light, it uses a whole grid of super sensitive microphones to record the tiniest details of sound waves right near where they're born. And then it uses that information to build a complete 3D map of the sound. Now, the secret sauce, the real superpower of this technique, is its ability to capture something called evanescent waves. These are incredibly detailed little sound ripples that only exist super close to the source. They're fragile. They fade away almost instantly as they travel out into the world, so you got to get your microphones right up in there to catch them. But if you do, they contain all the high-definition secrets about where that sound came from. And here is the truly mind-bending part. By grabbing those fleeting evanescent waves, this technique can see details that are smaller than a single wavelength of the sound itself. Now that is a huge deal. It's like having a camera that can zoom in with almost unlimited resolution, way beyond what any other method can do. It breaks the old rules. So the whole process is actually pretty straightforward. It happens in 3 steps. First, that grid of microphones gets up close and measures the sound field. Second, what's called a sound hologram captures all the important data, like how loud the waves are and what their phase is. And finally, a computer takes all that data and reconstructs it into a full 3D visual map. And just like that, the invisible becomes visible. But like any good detective story, there's always a twist. There's a complication, a red herring that can mess up the entire investigation and point our engineer detectives in the completely wrong direction. So here's the problem. This amazing sound camera, it works perfectly in a perfectly silent, padded, echo-free room, what scientists call an anechoic chamber. But that's not the real world, is it? The real world is messy. It's full of walls and floors and ceilings, and every single surface creates echoes and reflections. And all those reflections act like false clues in our mystery. The sound camera sees everything. The original sound coming from the source, sure, but also all the echoes bouncing back from every other direction. It can't tell the difference. So the final picture it creates gets all blurry and confused, mixing the real culprit in with a dozen imposters. And this, right here, is the breakthrough at the heart of the research. This is the missing piece of the puzzle. To solve this echo problem, the sound camera needed a brand new skill. It couldn't just measure sound pressure, which tells you how loud a sound is. It also needed to measure something called particle velocity, which tells you the direction the sound is actually flowing. Think of it like this. The old way, measuring sound pressure is like taking a still photograph. It tells you how bright the light is in one spot, but it doesn't tell you where the light came from. This new method, adding particle velocity, is like shooting a video. It actually shows you the movement, the flow of the sound waves. You can clearly see what's coming from the source versus what's just bouncing back at you. So by combining both of these measurements, the pressure and the velocity, the system can finally cut through all the confusion. It can mathematically separate the sound waves that are traveling away from the source from all those reflected waves traveling back towards it. It just erases all the false clues. And the result is, well, it's night and day. It's so dramatic. As you can see here, the old pressure-only method gives you this blurry, messy map where the real source is just lost in a sea of reflections. But the second you add particle velocity to the mix, the system filters out all that junk. And bam, the picture becomes crystal clear. The true source is perfectly isolated. The detective has finally caught the real culprit. Now, this isn't just some cool trick they can do in a lab. This has really profound implications for how we design and engineer the entire world around us. What this new method gives us is, for the first time ever, a 100% complete picture of the acoustic field. Engineers can finally get a full, totally unambiguous view of how sound actually behaves in complicated, real-world situations. So what does this mean for you and me? Well, it means quieter cars, planes, and trains, because engineers can hunt down and get rid of every single last rattle. It means concert halls that sound absolutely perfect, because they're designed with a complete understanding of acoustics. It means safer factories with less damaging noise, and even a deeper appreciation for music, as we can visualize exactly how a violin or a piano creates its beautiful sound. And it gets even cooler. With all this complete data, scientists can now calculate something called supersonic intensity. That's a fancy term, but it basically lets them predict which parts of a sound are going to travel the farthest. This helps engineers tackle huge problems like noise from a highway or an airport before they even become a real issue. As the lead researcher, Dr. Efren Fernandez-Grande, put it, this study helps us gain a better understanding of the potential of combining these two measurements. It's a huge foundational step forward in a really complex field. So in the end, we've taken something that was an invisible annoyance and turned it into a visible, solvable problem. By learning to see sound with this incredible new clarity, we're not just making our world quieter. We're literally opening up a new window of perception. And that just leaves you with one final, exciting thought. What other invisible forces out there will we learn to see next?